Welcome to the Astronomy 105 Lab 9. This is ages and distances to clusters. There are some documents that you have to have outside of this that aren't in your lab manual, but we will be posting those on D2L for you, so just go ahead and keep an eye out for that. So here's our stellar main sequence lifetime. There's a lot of cool stuff we can tell you about HR diagrams, which we talked about last time. Here we have luminosity, which you could also have absolute magnitude, just a reminder. And down here we have surface temperature in Kelvin. You can also see there's spectral class, that "Oh, be a fine girl, kiss me." You would also have color, which you can kind of see that color range represented right there. So all three of those are acceptable ways to determine temperature, and those are all acceptable things for an HR diagram. Now, a big thing about HR diagrams is they do not use apparent magnitude. So this is luminosity, which is great, but if this was apparent magnitude, it would not be an HR diagram anymore. So here we can see a bunch of stars are plotted. We have some very, very hot, bright O stars, which we don't actually see really any of those. They're not common, but we do start seeing a lot more B stars and A stars, and you can actually see that this main sequence here has a bit of a thickness to it. We're going to talk about that just a little bit more later, but while stars are on the main sequence, they do actually get just a little bit brighter and rise up on the main sequence just a little bit. And you can see that there are a lot more M stars, which are much cooler, than there are O, B, and A stars. Very hot stars. You can see some giants, this is where they would lie, some supergiants, the white dwarfs would be down there. And all this, I'm not going to spend very much time on this, but all this comes because of their different properties. So massive stars, these O, B, A stars, form very quickly, and because of that, they also die very quickly. They use up their fuel, and they leave the main sequence a lot faster. Low mass stars, these ones down here, they form a lot slower, and they also last a much longer time, magnitudes difference. So while they're on the main sequence, they're fusing hydrogen in their cores, and the high mass stars do that really fast, so they burn really bright, but not for very long. The low mass stars do it much slower, so they're not quite as bright, but they last a much longer time. The giant stars you see in this upper right-hand corner are stars that have exhausted their core hydrogen and they have expanded. Right, so all that is stuff that you really talk about in lecture. We don't really talk too much about it in lab, just briefly going over it. All right, so here we have some main sequence lifetimes. Now, I personally like to write out these numbers because they're really big numbers and they don't necessarily make sense just saying, oh look, the star here has a lifetime of 10 to the 7 years. What does that mean? Well, it means that you can write a 1 and then write 7 zeros behind it, and that's how long this star is. It's quite a long time. Let's see if I can draw it for you guys. 10. Beautiful. My zeros are going to look horrible, and I'm very sorry about that. But, you know, you'll learn something, hopefully. Getting a little bit better, maybe. Maybe not. So that's a one with 7 zeros behind it, right? So we can see that that is 10 million, right? Thousands, millions. Yeah, 10 million. So these stars last about 10 million years. But if we go just a little bit cooler, we get into the B stars. They suddenly last 100 million years. So that is a pretty large difference. It's an entire magnitude's difference. Now these stars down here, starting to get into the A stars, last 10 to the ninth, meaning that you have one with 9 zeros behind it. That is 1 billion years. It's a pretty long time, but, you know, not compared to some of these down here. Our sun, for instance, has a lifetime of about 10 to the 10 years. So it's 10 billion, and our sun is about, halfway through its lifetime. Next, we have these K stars, which are 10 to the 11. So, we're starting to get into it. We have the hundreds, thousands, millions. We're at 100 billion right now. These ones, they could last even longer. So they are on there for a very long time. The cooler the star is, the lower mass it is, the longer it lasts. And you can really see that age here looking at the difference, because we started with 1, 2, 3, 4, 5, 6, 7. We started with this many zeros. So may not seem like a big difference, but it really is. All right. Now, we did talk last time about some common properties of stars in a cluster. Last time we were trying to find distances, so the most important thing to us was that the distance, stars in a cluster are about the same distance away. But this time we're trying to also find, their ages. So we're going to review these again. The common properties for stars in a cluster are their distance, because they're all a similar distance away from each other, and therefore from us. An age, because they were all made at about the same time from the same stardust, the dust and gas, all that material. So they also have a very similar chemical composition. So age, chemical composition, distance, all the same for stars in a cluster, but each star in a cluster can be whatever temperature and whatever size it wants to be. So you can have a lot of red, low mass stars, and you can have a few of those much brighter blue stars. But we remember that we just learned the blue stars burn out much quicker than the red stars do, so that can help us determine age, and we're going to see how that happens. So this cluster here is going to be your favorite cluster by the end of this, I hope. This is the Pleiades cluster, and you can see a lot of really bright blue stars. That is because this is an incredibly young cluster, and you can still see those blue stars. They haven't died yet. They're still on the main sequence, and it's really nice. There are also red stars and yellow stars and orange stars there, but we just tend to see the brightest things, and that brightness covers up a lot of other stuff. So let's look at this beautiful diagram here. Luminosity and surface temperature. So this is an HR diagram. We have our standard main sequence plotted, and we can do a cool thing here. So we plotted all the stars from this cluster on our graph, and if we start from the tippy top of our main sequence and we work our way down, we can eventually get to the point where there are stars on the main sequence from this cluster. We call this the main sequence turn-off point, because it's where these stars start to peel off of the main sequence, and this is where we determine how old the cluster is, because we know how long these stars stay on the main sequence. So if they're starting to come off, we know that they're at the end of their main sequence lifespan, and we can determine that the entire cluster, because stars in a cluster are the same age, we determine that the entire cluster is the same age as right there, which in this case is 100 million years. Now, you may notice that these stars down here are red stars that are not on the main sequence. This is not because they're starting to come off and become giants. This is actually because the Pleiades is so young that those stars actually haven't finished forming yet. So they're not fully formed, and so they're still just a little bit brighter and not on the main sequence yet. All right. So, moral of the story, you're going to be using the main sequence turn-off point to determine the age of a cluster. Now, that's not all we're doing today, but let me go ahead and show you an example of something that's a little bit older. So we have our main sequence. Again, we start at the top, we work our way down until we see stars that are in fact on the main sequence, I would say that it's right about here. So you can see some stars there. This is the main sequence turnoff point. Now, in the Pleiades here, you can see it has a very high main sequence turnoff point. There are lots of blue stars, and you can just in general tell that this is a much younger cluster, right? There aren't many giant stars, or really, there's not any giant stars over here that are red giants or anything. And, it's still forming stars. This is very young. Now down here, you can see that it has a much lower main sequence turnoff point. It does not have nearly as many blue stars. You can see a lot more of these red stars, and even the red stars are becoming red giants. So these are some telltale signs that let you know that this is an older cluster. If you find the main sequence turnoff point and determine the age of those stars, you can infer what the age of the cluster is. In this case, it's about 10 billion years. All right, so we use the main sequence turnoff point to determine the age of the cluster. Now here is something interesting. We have something called the ZAMS line. This ZAMS line means zero age main sequence. Remember at the beginning I talked about how there is a thickness to the main sequence and how even when the stars are on the main sequence, they do tend to get just a little bit brighter during their main sequence lifetime. Well, this helps us account for that. This is the zero age, so at the very beginning, it goes right along the bottom of the main sequence. That's important because later when we do the activity, you want to make sure you line up your ZAMS line with the bottom of your main sequence. Now I have a bunch of clusters plotted here. You can see Pleiades is incredibly young. It has a very high main sequence turnoff point, but the lower the main sequence turnoff point here, the older the cluster is. We dealt with Hyades last week, I believe. M3 is a very old cluster. M67 is also a very old cluster. So you can see they have much lower main sequence turnoff points. Also, be aware that this graph here is logarithmic. So you read it in a little bit of a different way. The numbers get much closer together the closer you get to the next interval. Don't let that trip you up. It's not that hard. Well, we did talk about this last time, the interstellar dust, but this time we are actually going to account for our dust. So, dust and gas like to scatter our blue light. When that happens, it has two effects. The first is that because it's scattering blue light, you see more red light, and you think that the star is cooler because it looks redder. The second is that because it is scattering light, it is making the intensity of the light that you do see dimmer, right? So you don't see as much light, and you think that star is dimmer, and therefore you think it is further away. Now, we do have to account for that, and we will be showing you how to do that in this lab. That doesn't really apply now because, well, you're online now. You can write on whatever you want. So this is your chart. We're going to be doing M45 all together, so you guys can pay attention, write all these answers as we go along, and get some free points. It'll be great. So this is M45. If you have any guesses as to what M45 is, you might guess that it is the Pleiades, and you would be correct. We love the Pleiades here. We like to talk about it a lot. So we're going to do these columns in order because they're set up in a beautiful order that really help us, do this in an easy manner. So we'll start with distance modulus, which is apparent magnitude minus absolute magnitude. Always apparent minus absolute. So we have our apparent magnitude on one side, so this is not an HR diagram. It's a color magnitude diagram. This is M45 Pleiades. We have all those stars are plotted. And you may notice on the top it says standard color index, and on the bottom it says observed color index. This is how we will be determining the dust. All right, this is how we'll do it. I'll get to that in a little bit. First, we wanted the distance modulus, right? So we have our apparent magnitude here, the little mv. Remember, the v is just a subscript meaning visual spectrum. And we have an overlay. So you take your overlay and you have to line up. It has standard color index on the top and standard color index on the bottom. And it has absolute magnitude on the side. So this is an HR diagram. It's really nice. We have absolute magnitude. On our bottom layer, we have the apparent magnitude. And so we can find a distance modulus if we have those two things. So we're going to line up our overlay here at the very top where the scales are the same, standard color index. You'll line it up 0, 0. Make sure that's all good. Then you're going to move the overlay vertically. Do not move it horizontally because you don't want to mess up your 0, 0. So you move it vertically up until the cluster sits right along the bottom, or the line sits right along the bottom of the cluster. This can be a little difficult for some of the clusters. So if you have questions, you maybe want to like screenshot or take picture or something of how you're doing it and send it to me. I can help answer questions and tell you like, yes, that looks really good, or you might want to go a little higher or lower. All right, now that this is in place, we can find, we actually get a few different pieces of information here, but what we're looking for right now is distance modulus. So we look where the 0 is on our absolute magnitude. We're just going to read off whatever number that is in the apparent magnitude. Remember, this is going backwards, so to speak. So here's 5, there's 6, there's 7. Looks like it's kind of close to 6, so I'd say about 5.7, 5.8, right? We marked it as 5.7. So you write that down in your graph. Beautiful. The next thing is we need to figure out the distance in parsecs using our distance modulus. Instead of doing a bunch of math, we gave you an easier way of doing it by using a graph. Look at this beautiful graph. So you use the distance modulus down here, you mark where 5.7 is, right? You go up to the line, and then you go over, and we mark it as about 130 parsecs. Right, very easy to read. This is a logarithmic graph, so it is a little more difficult than just a normal graph, but you shouldn't have too many problems. Just do your best, give it your best shot. All right. So we mark down it's 130. We write it down in our graph. Next thing says color excess. So now I don't really like how the slides show this because you see how the standard color index is the same here. You always keep that in line. What you're going to be measuring is standard and observed, the difference between those two. But I don't like that you have to move the page up and then do that. Instead, what I like to do is get that piece of information first. So when you first line up your standard color index and they're all on the same line, just look down here at the bottom and measure the difference between those two. And then write it down in color excess. It's a lot easier to me that way. Do it however makes sense to you, but I just think it's easier without having to add that vertical element. You can just look horizontally. Now to get back to where we were. You're just going to read off the page what the difference between those two is. In this case, we say that it's 0.05. Do try to get as many decimal places as you can. In this case, about 2, maybe 3, but really about 2. Also remember that this is 0.0. This tiny line would be 0.2. This big line is 0.4. So in between here is 0.1, and then in between there is 0.05. So just be aware it's not broken up into every tenth. It is broken up a little differently. Don't want that tripping anyone up. So we write down our color excess as 0.05. Boom. The next column says A equals 3 times CE. What this stands for is A is absorption factor, which is what we're looking for, equals 3, which is the number 3, times CE for color excess, right? So you multiply this by 3. Put it in a calculator. It's very easy. You get 0.15. Now the next column says distance modulus corrected. So your distance modulus minus your absorption factor. here's your distance modulus, here's your absorption factor, you subtract them, and you get 5.55. Now, the same way we found the distance earlier, using the graph in parsecs, you're going to find the corrected distance. So now, instead of using 5.7, you're going to use 5.55 and correct that distance in parsecs. You already saw how to use the graph. We now say it's 120 parsecs. All right, now, to convert it from parsecs to light years, 1 parsec equals 3.26 light years. So I personally like to just write here times 3.26. Oh, can't see my decimal. Hold on, I'll make it a little bigger. It's really bad handwriting, I'm sorry. I'm using a trackpad. Maybe it'll get better one day. So we multiply this number here by 3.26 and we get our distance in light years. Great. We found the distance. Now the only thing we have to find is the age. And to do that, remember we use the main sequence turnoff point. So we're going to go back to our graph one last time. Make sure it's still set up with the 0, 0 at the top when you swooshed it up vertically to get the ZAMS line just underneath the cluster. And now you're going to look at the top scale, all right? You can look at the bottom because there's a standard color index at the bottom as well, but I think it's a little more confusing to remember which one to look at. So instead, I like to just look at the top because it says standard color index for both of them. So it's the same scale. It's not going to matter which graph you look at, the overlay or the paper. So you're going to start at the top of the ZAMS line, work your way down until you see the stars are actually on the ZAMS line. I personally think it would be a little up here, but yeah, we said it's right in this area, right? So then, once you find that, you're just going to, get a straight edge to make sure you do this fully vertically, and you're going to say what this color index is for that point. I know in the slide it says to look down, but again, I prefer to look up because it's the same scale for both. We said that it was negative 0.01. It is very tiny, and that's okay. Pleiades is very close to us, and it's very young, and there are things that are a lot further away, so it's not necessarily always going to be that small of a difference. So, color the turnoff point, negative 0.01. We write that number down. And then we have one more graph to look at. This one is a little harder to read. We're going to look at the standard color of the main sequence turnoff point. You find where your number is. We put it right here. Again, you go up to wherever the line is on the graph and over. In this case, it's 1 times 10 to the 8 years. I say this is a little harder to read because not only is it logarithmic, but also it's in scientific notation. The reason that this is 1 times 10 to the 8 is because you're exactly on that line there. If you were to say be a little higher, say you were here, you could say that this was 3.5 times 10 to the 8. So you're always going to look downwards, okay? You can have some times 10 to the 6, I guess, but it would be very high numbers times 10 to the 6. You cannot have any times 10 to the 10. Our line doesn't even reach up that high because there should not be any times 10 to the 10 numbers, all right? If you think it's going to be times 10 to the 10, you're probably reading it backwards and it needs to be times 10 to the 9, all right? That is a little bit harder to read of a graph. If you have questions, please ask. I know we're all available to answer questions, and that can be a little tricky. But hopefully this example has helped. You just write down 1 times 10 to the 8 years in this little spot here. I mean, well, the years is already taken care of for you. So it's 1 times 10 to the 8, and then you're done with that row, and you go on and do the other clusters. I would like to mention that the online lab manual does different clusters than the in-class lab manual. So my suggestion is to do the online lab manual clusters because, well, they were chosen for the online labs. We will be providing some outside resources, as I said before, so don't worry too much about that. If you do need help, just ask us. We can try and work things out, and uh, we are always trying to help answer your questions. All right, hope this helped.